Hi, my name is Firas Mrad, and I will start this presentation. So this video is going to discuss the basic relationship between processors and their memory. At a high level, we can think of the processor as a block that communicates with memory through a couple of signals. It provides memory with an address that it either wants to read or write, and then depending on whether it's reading or writing data, either memory changes its data based off the inputs from the processor, or the memory returns a piece of data back to the processor. In an ideal situation, the processor and memory operate in similar speeds, and ideally, that similar speed would mean that a memory read or write could happen in a single processor clock cycle, so that anytime a processor requests a piece of data, the memory returns it in a single cycle. Unfortunately, that hasn't been true for over 30 years. This figure here shows the relative speed or performance of both processors and memory over the last 30 years. And you can see that while the processor performance has grown exponentially, memory performance has grown much slower than that. And so while back in the 1980s, memory and processors might have had similar performance, these days, there is a very large gap between the speed and performance of a microprocessor and the speed of memory. And so the challenge that designers have to deal with is how do we make a memory system that appears to be ideal, one that is fast, cheap, and also has a large capacity. The real challenge is that there is no existing technology that provides all three of these features. Indeed, this table shows the three common types of memory technologies available, and each of these different technologies have different trade-offs. So an SRAM is very fast, and so could achieve the speed that would be desired, but storing information in an SRAM consumes a fairly large amounts of area and space, and it also was fairly expensive to store a bit compared to some other technologies. Another technology that you can look at is the DRAM or dynamic RAM. It's more dense than an SRAM, but is also slower. With the DRAM, you're not quite as fast as you need to be to keep in track with the processor, and that is actually what the previous figure was showing. It was the DRAM versus the processor. Even slower than that is our disks, which are very dense and very cheap in terms of their cost per bits, but are even slower than DRAMs are. And so the solution to creating our semi-ideal, fast, cheap, and large memory is to use a hierarchy of memory to try to approximate this ideal, to try to get the benefits of the fastest RAM with the higher densities of a DRAM or a disk. And to do this, we create a hierarchy of memory with the microprocessor sitting at the top, and just below that, we put some fast SRAM, which we refer to as the cache near the microprocessor. Below that, we have some main memory composed of DRAM, and below that, we have finally what is referred to as virtual memory, which is usually composed of some sort of disk. It could be a hard disk drive or more recent solid state drives. But in any case of these different technologies, each one of them have different trade-offs in speed and capacity. So we put the fast but fairly small caches near the microprocessor, and then we put larger and larger but slower memories further away from the processor. And the hope is that most of our access to memory from the microprocessor will hit in the levels close to the microprocessor. So hopefully, most of them will hit in the fast cache or the fast SRAM. And so to the microprocessor, it will appear that our memory is fast, but also has the capacity of larger lower levels. So now Marc will present to us how this memory hierarchy would work.
Hello everyone, I'm Marc Mefleh, and I will continue what Firas already started. So as Firas said, the only way that this memory hierarchy can work is if we actually are able to access or find most of our information in the small and fast SRAM, and most of the time this works because programs and memory references tend to exhibit localized access to memory. So this is generally true. However, it's not always guaranteed for all programs, and which is why there can be variability between different programs and how well they make us use of memory hierarchy. So as an example of how hierarchy works, okay. So as an example of how hierarchy works, this is an example of a C code, which is basically summing up all of the values in an array. And if we were to look at how this program would access the values in memory over time, we would find that the values of my array are the first iteration through the loop, and it would access the first element, so my array 0, and it will access the second element, so my array 1 during the second iteration, and then it will access the third element during the third iteration, which is my array 2, and so on. And this would continue on, and so this example here shows an example of what's referred to as spatial locality. And so spatial locality is that if you have used data recently, then you are likely to use this data. No, you will use data close to it soon as well. And for example, in this case, we accessed my array 0, then we immediately accessed my array 1. So this is an example of spatial locality. Spatial locality also allows us to exploit memory. So we can access some data we want and bring it nearby data into higher levels of the memory along it with it. So that was an example of one type of locality. Another type of locality we can observe is with this code. So this is we look at this at the instructions that would be executed that have to be accessed from memory. So if it was to expand this C code to assembly code, this shows one example of how this could be implemented in MIPS. And if we were to look at how these instructions would be accessed from memory over time, we would see that the first loop through the loop, so sorry, the first time through the loop, we first access the first instruction. So let me annotate here. We will access the first instruction, and then we will access the second instruction, then the third, then the fourth, the fifth, the sixth, until we got to the jump, and then after the jump, we would go back to the beginning of the loop. So here, then the second one, then the third one, and we basically repeat the same thing, accessing the same instructions in a row. And so if we look at this, we can see that a particular instruction is actually accessed repeatedly over time. And this leads to the idea of what's referred to as temporal locality. And George will discuss more what's temporal locality. Thank you, everyone.
My name is Aynati, and I'm the third member of this group. What Marc has just explained leads to the idea of what's commonly known as temporal locality. But what exactly is temporal locality? If data was used recently, it is likely that we'll use it again soon. To exploit this, we want to keep recently accessed data in high levels of the memory hierarchy. Although temporal locality may seem like a simple and obvious concept, it is one of the most important memory intelligence. Finally, to quantize how well a particular memory hierarchy is doing, we have a couple of common metrics that we use. First off, some terminology. We say that something is ahead in a particular level of the hierarchy if it is found in that level of height of the hierarchy. So if we look for an address and it is found in the cache, then we say it is a cache hit. If it is found in main memory, we say it hits in main memory. Alternatively, if it is not found in a given level of the hierarchy, then it's called a miss. This means that we have to go to the next level of the hierarchy. So we are interested in how often we are hitting or missing in a particular level of the hierarchy. We refer to this as the hit rate or the miss rate. So the hit rate is number of hits over the overall number of accesses. You could also calculate this if you know the miss rate. So if you know the miss rate, you could say that the hit rate is 1 minus the miss rate. Because anytime you're missing, it means you're not hitting. Similarly, for the miss rate, it's the number of misses divided by number of accesses. You could also compute it using the hit rate. So it's 1 minus the hit rate. This gives us an idea of how well locality is being exploited to be able to find most of the instruction in our cache or in our main memory. Along with hits, we are also interested in how long on average it takes us to access data when the processor asks for a piece of data or instruction. This is referred to as the average memory access time. We will see how we would calculate this if we had a system with the three levels that we showed before. So one level of cache, main memory, and then virtual memory beyond it. First, every access would have to go to the cache to see if it's there. So we have the time to access the cache, Tcache. If it doesn't hit in the cache, meaning we miss in the cache, we have to look at the miss rate for the cache, MR cache. So if it misses in the cache, we have to go to the next level, which in this example is the main memory, which would be for all the times we miss, the time to access the cache plus the time to access the main memory, TMM. And further, if we miss in the main memory, MRMM, we would have to go to the last level, which is our virtual memory, and get the data there, hence TVM. So an equation like this would show how we could calculate the average memory access time for a system with one level of cache, main memory, and then virtual memory. Thank you for your time. This was presented by Marc Mefleh, Firas Mrad, and Aynati.